and it requires infinite band. So you can kind of the impulse function is a zero width rect function. And if you look at that, you end up with 1 over 0. And again, it goes back to the comment about rapidly changing signals. You can't get anything more rapid changing than an impulse function. And it requires every ounce of frequency. Did you ever see this signal in real life? It's just a mathematical creation. But we use it a lot to model things as an approximation. Okay.
Does that zero pulse width is in the time dimension because it's only, I mean in the time domain because it's only that one little line, right?
Yeah.
Okay.
You can think of that as tau. Tau goes to 0.
And that's a 0 in the denominator?
Yeah.
So it's, okay.
Over in the, yeah.
So it's just like as that gets very small and goes to 0, it goes to infinity, like that kind of relationship?
Yeah, remember we had the first zero crossing was 2 pi over tau. So I put 0 here, that means that this thing goes out to infinity. So you could say that I'm really just drawing a sine over x function, but it just never goes down to a 0 crossing.
Cool.
Any other questions? We only got about halfway through the notes. So the other things I was going to cover are some of the properties of Fourier transform. These are things you've seen before. Linearity. Duality is something you probably haven't seen before. We'll talk about that next time. Scaling. Right? We've talked about scaling when we did Laplace. Time shift. We've talked about that already. It also applies to Fourier. Frequency shift also applies. So, those things I won't cover in class next time, but the duality. All right, and then think about Monday. We'll make a decision which way we go, project or file. Have a good weekend. Look at that paper by Brad Story. It's interesting to see.
Cool. The second homework ever.
Oh, from last year?
Yeah. Simplifying basic.
Yeah, people are like, oh my God, can you help me study this whole test? I probably took it.